Nyquist plot. Nyquist plot is open loop frequency response plot to find the closed loop system stability of the system. Now, Nyquist plot uses polar plot as its basic plot. We know already how to plot the polar plot. Nyquist plot uses Nyquist stability criterion. So, Nyquist plot never depends on the gain margin, phase margin concept. So, it has its own Nyquist stability criterion based on principle of argument. It's an argument principle. Now, Nyquist plot can be used for all type of systems. Let us say if open loop system is a minimum phase transfer function or non-minimum phase transfer function, then we can find out the closed loop system stability. Sometimes Nyquist plot can be used to find the stability of non-linear systems with the non-linearity is very minimum, and also we can analyze the system if at all if you have time delay in the system. So Nyquist plot uses the concept of principle of argument to find the stability accurately for time delay systems. Now we'll see what is Nyquist stability criteria and what is the basic principle behind it. So let us consider a closed loop transfer function, a closed loop block diagram of the system like this. So we have a g of s is open loop, we can say it's a forward path transfer function, and h of s is my feedback path transfer function, and this input and output. This is a closed loop block diagram of a typical control system. Now first of all, take what is the open loop transfer function. So we know the open loop transfer function, loop transfer function is nothing but g of s into h of s or simply gh of s. So I am representing gh of s as gh of s is equal to n naught of s by d naught of s. This naught gives the open loop. So n naught of s by d naught of s is the open loop transfer function. Now let us write what is called characteristic function. So my characteristic function q of s, I am writing it as 1 plus gh of s. It is not the characteristic equation. If it is equation, 1 plus gh is equal to 0. But I am interested on only characteristic function. So let us look at that function. How can you write that q of s is equal to 1 plus gh of s, that is n naught of s by d naught of s. Then we can write q of s as a numerator. We have your d naught of s plus n naught of s divided by your d naught of s. So denominator of this and denominator of open loop transfer function is same, d naught of s, d naught of s, whereas the numerator of this is going to be d naught of s plus n naught of s. Now what I am interested is, I am interested on the characteristic function q of s. Okay. Look at what are the poles of this q of s function. Just now I said the poles of q of s function are roots of d naught of s, which are nothing but my poles of the open loop transfer function. Then I can make a statement like this: the poles of q of s function are nothing but the poles of open loop transfer function. Poles of q of s function are open loop poles. Now let us write the characteristic equation. 1 plus gh is equal to 0. Then when you do this, you will be getting it as a d naught of s plus your n naught of s is equal to 0, and roots of these are nothing but my closed loop poles. Now closed loop poles are nothing but roots of characteristic equation, and that equation we are getting it as a d naught of s, n naught of s is 0. But what is this? This is nothing but my numerator of q of s function. Now I can write like this: the zeros of q of s function are nothing but closed loop poles of the transfer function. Closed loop poles means the poles of the closed loop transfer function. What we are interested finally are the location of the closed loop poles, because if any pole is lying in right of the S-plane, system is unstable. If the poles are an imaginary non-repeated, system is marginally stable. If all the poles lying in left of the S-plane, system is stable. So finally we want how many poles that are lying in the right of the S-plane. So if no poles are lying in right of the S-plane, which is my system is stable, that I want to find. For that what I need the characteristic equation roots or else the zeros of the q of s function. So zeros of q of s function is very important to me. Now again, so we can write 1 plus gh of s is nothing but my q of s. Then how can I write gh of s? Gh of s is equal to q of s minus 1. This is also very important. GH of S is Q of S minus 1. So finally I can observe three things out of this analysis. The first thing is the zeros of transfer Q of S function are nothing but my closed loop poles, and the poles of Q of S function are open loop poles, and my GH of S you can write it as Q of S minus 1. Now we know that Nyquist stability criteria uses the concept of principle of argument. Let us look at what is the principle of argument. I'll give you the statement first, then we'll see the analysis next. The principle of argument is used to map an arbitrary contour, that is a closed path, from S plane to f of S plane, where f of S is a complex variable function with S is a variable parameter, and usually the principle of argument is given by n is equal to p minus z. What is n? N is number of encirclement in anti-clockwise direction around the origin. P is number of poles encircled by the enclosed by the arbitrary contour. Z is the number of zeros of function f of S enclosed by the arbitrary contour. Now depending upon the P and Z, then I can find out what are the number of encirclements. The other way, if you know number of encirclements and if you know P, you can find out the Z. So out of these two parameters, if you know two, the third one we can find out. So this principle of argument can be used to find the closed loop system stability. Let us closely observe how can you derive this n is equal to P minus Z.